Hey guys, here we go again, and this time we're going to start building a PLC program with the TIA portal from the very beginning to a point where beginners level ends, where we're starting to write and building and downloading and testing, debugging a little bit of a debug of a PLC program. First, we're going to start with a new project, name the project, pick the uh, location, author, if any comments, just click create. We're going to wait for it to build the project for us. Now the project is empty. We don't have any devices. We don't have anything. We can add some securities and some stuff. However, we have to add some devices. The two most important devices that we have to add are the PLC and the HMI. We go with the PLC. We're going to start with a 1500 PLC. If you look at here, PLCs with respect to the power they have, they're numbered. The 1200 are the low end kind of PLCs. They're low end to the applications. They may not be low end to your application. If your application is not a big size machine, if your application does not require high speed, if your application does not interact with many devices, many external devices, you're okay with the 1200. The 1500 is where the machine is really big. The machine needs some power. And later in this series, in the advanced level, probably we're going to talk about how we can size our PLCs to match the power of or the requirement of the machine that we have. Then we're going to look at what things mean. So 511 or 1511 PN, that's Profinet, and then PNDP, that's Profinet and Profibus. And then we have a lot of abbreviations. What we're looking for in many of these types of PLCs, if we open the 15 and then the number is how many ports you have for Profinet. What we're going to be looking for is a safety PLC. The safety PLC does not necessarily have built-in safety IOs, where it necessarily has the capability of having a safety program that is capable of interfacing with any safety IO device, whether it's integrated to the bus of the PLC or external to the PLC, like on a ProfiSafe level. Now we're going to be looking at the different types of PLCs where we can find the F letter, and that F letter is basically saying that it's a fail-safe type of PLC. I'm going to take or don't look at the F letter, look at the yellow color on the PLC icon right here. The 1515F. I'm going to look at what these guys have in different. They're all the same. The version of the PLC is different. I'm going to go ahead with this latest one and let's see what they have. Sometimes you don't even feel there's any difference. But if we're going from a version to another version, that means the made of it and the make of it and the supported. There are some supported software packages and capabilities built in the PLC that you may need and you may not need, really. If you're a beginner If your application is not that complex, you're not going to need those. I mean, by those, the add-on capabilities that would likely to be added to the PLC. Now, uh, after we created the PLC, this screen would pop up, and this screen will guide us through several steps. And these steps, we're going to start with the protection, the protection of the PLC. In our case, we're going to do 1, 2, 3, 4, 5, 6 kind of protection password with this PLC. So I'm going to go 1, 2, 3, 4, 5, 6. The password contains at least 8 characters. Okay, we can go 7, 8. Not to exceed the minimum. Not to exceed the maximum 120. The password must, what is that? At least one number, must contain at least one lowercase and one uppercase letter. Okay, we're going to go A caps, B small, 1, 2, 3, 4, 5, 6, 7, 8. A caps, B small, 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are a few things to notice here. This password will allow us to do anything in the PLC. If we want to access the PLC or configure it or debug it, if we set up this password, we're gonna have to have the password for programming, for debugging, for monitoring the PLC with any TIA portal project. So I'm locking the PLC with this guy. Okay, so I'm going to disable this one. When I want to disable it, it's asking me for this password. Put it again. So I just disabled the password. So this is basically what it's saying. It's the password. Only secure PGPC allowed. Yes, only allow secure PGPC and HMI communication. Yeah, this is important. So we can so the HMI communication to the PLC will be encoded or encrypted. The TI portal to the PLC will be encrypted for extra security in case the project you're working on is a little higher security than the normal shop project. So this is required for some industrial applications if they require some securities, or sometimes some aerospace applications require this to be set up. It doesn't hurt to put it in. Okay, PLC access, full access include fail safe, full access no protection. These are the low protection level. Read access, users have read access only. PLC configuration, users can also change PLC operating state. That means turn it on and off. So if we're looking at building a fail-safe or a access control to the PLC, this is what we're going to use. What we're going to do here, no protection, anyone can access the PLC regardless. If we do this, complete protection, people need password to even connect to the PLC. Nobody can connect to the PLC. Nobody can see anything that is in addition to this guy. So we're going to take that out for our beginners level sake, and then in some other levels uh, we will look into these capabilities a little deeper to show what kind of different application requires what different levels of access and what different kind of securities. Overview, we're good here. So this is our PLC and this is the PLC rack. Now at this point, we can add I/O blocks. We can add all kinds of different blocks in this PLC. A few things, since we're talking about PLC, you're a beginner. You're still responsible for building this PLC. And when you get the prints, you will see the I/O blocks sorted out in a specific way. And the way we prefer to have the I/O blocks sorted is, for example, all the inputs, and then all the where is it? All the safety outputs, and then the safety input. And then we do all the outputs. Okay, so regular input or standard input, safety output or fail-safe output, fail-safe input, then the regular or standard output. The reason we do this is because the standard inputs, we never want to lose those. So we're not going to turn these off in any safety situation. We're looking for standard inputs. Safety outputs, we're never going to turn these off in a safety situation. These are controlled by the safety program only, so we're not going to turn them off. These turn on the machine. So even in the safety in a fail-safe situation, these are the outputs that turn that brings the power to the machine, and that's what we want to keep separated from all the fail-safe situations. These are controlled by the safety program only, and they can turn on or off regardless the safety situation. These turn on and off depending on the safety program and how the safety program is running. Then we go to the safety inputs. These safety inputs are the ones that we read and now, if in case we want to have the safety driven by some sort of hardware or safety hardware capability, what we're going to do is we're going to set this safety module to cut off output power to this output module. Now we can do that. That is why we put safety outputs after the safety inputs. That's basically it. Then, in my case, I'm not going to use any of these. So I will, we can leave them. Okay. Then when we come here, in this module, I'm looking at the standard inputs. These are the addresses. Standard inputs, safety output. These are the addresses. You can see the safety output has an input module in it. We don't use these. These are for later when we program the safety, when we do the safety program, you will understand what these inputs are for. Basically, we're reading the status of the safety outputs with of the safety module with these IOs. The safety input, same thing. You'll see why we have the outputs for the safety input, because we're basically telling it to turn on the internal relay that passes the power to the outputs of this, or of the modules behind it, basically it. Then we look at the standard output module. We can change this to, for example, if we say 5, it will tell me no, because you're still here. And if I say 2, or maybe 1. So basically that's the way it is. These are the internal modules in this PLC. Then I add another device, and that is an HMI. We're going to take a look at the unified HMI for this example, and we're using unified 17.8. When that's added, if I press on this show addresses and labels, you can see the PLC has 2 different networks, and it's up to me where I want to connect the HMI to. And the HMI has 2 different networks. Right now they're not connected. What I can do is grab this guy and connect it here or here, and it will change everything in the HMI configuration. However, I don't normally do that. What I normally do is to get a tag transferred from the PLC to the HMI, and that will trigger the whole process in the background to connect and set up that connection between the PLC and the HMI. And let's do that real quick, and you'll see what I mean by. So we're going to call it HMI setup, and this HMI setup is basically a memory bit, and we're going to say it's 10 by 0. Okay. Now I open the tag list in the HMI, show all tags, put them next to each other. Okay. Take this guy, transfer it here. Okay. Now we're going to go back to where my hardware configuration is happening. Come on. You can tell that this is a connection that started happening between port number 1, that's the Profinet, port number 1 in the PLC, and port number 1 in the HMI, and this is where we got our connection all set up, ready to go in the between the PLC and the HMI. Okay. Now that the connection is all set, what I'm going to do is go to the HMI tags, delete this guy, I don't need it anymore, and then delete this guy. My HMI and PLC are still connected, At this point, if I go to the devices and networks, they're all connected. What are the IP addresses? Click here. You can tell what the IP addresses are. Okay. Now we go to writing our first logic blocks. Now let's take a look at this list right here. What I need you to know is OB1 is that object block 1 is the main block in the PLC, one of the main blocks in the PLC, and they call it organization blocks. The organization blocks that you see here are these blocks that the PLC will run them regardless your software control. So some of them are like for the first one, this first one is OB1. This first OB1 or program cycle is the one that runs all the time and calling every other, and you have to call every other function through this block when you write a program. So if you write a function or function block or whatever you want to write, you have to put a call in OB1 for that function for it to be actually running. Otherwise, it's not going to be running. Then you have the startup. This OB is basically running only during the startup cycle. So there's one cycle, one scan cycle of the PLC. If you turn this OB on or add this OB, it will run only during that scan cycle. One cycle, and it will turn off. Time delay interrupt, cyclic interrupt, hardware interrupt, all kind of diagnostics, pull and plug of modules, rack or station failure, programming error. So basically, this OB is called if an error in the program or fatal error like dividing by 0 or something like that, that's supposed to stop the PLC. Instead of stopping the PLC, it will call this block. And what we normally do when we're faced with this kind of stuff, we add this block and we add some logic in there that will allow us to revive the PLC without connecting to it. IO excess error, time of the day, all kind of different organization blocks that will allow us to do things that are related to the hardware or related to the PLC itself from a hardware perspective or from a software perspective. But these are the basics and main objects or organization blocks that allow us to do certain functions to our PLC. Function blocks, these are the equivalent of classes in software. If you're familiar with software, basically the idea here is you have a program that's running and it has its own data attached to the program. So you don't need to feed it with data. It has its own data. Sometimes we do feed it with data if it's required, but it has its own data. And we will see later what do we mean by that when we say it has its own data. A function, it's only a code that needs input and output data to actually process. Otherwise, it will not be able to do anything useful without having some data, some external data fed to it. Data blocks, it's one of the methods of the different methods that data or variables or parameters are stored in the PLC. And in Siemens case, they call them data blocks. And the other method is called memory memory variables. Memory variables are more of a global. Data blocks are also global, but they're more structured kind of data. So that's the idea. What we're going to do here is we're going to start with a function block, and let's not go fancy in here, and we're going to start with ladder logic type of function block. So function blocks, as we said, they have their own data, and their data is basically the data that we're talking about is stored in here in the statics. Now the static variables are stored data or stored variables inside the that function block or inside the data attached to the function block. And what we're going to do here is pretty simple. We're going to say I have an input. I'm going to call it A. And then what I'm going to say is I have a timer. And then that timer, instead of having a single instant, and that's a global variable outside the function block, I'm going to say a multi-instance. And what I'm going to say here is a timer. And if you can see, we just added that inside the function block and we called it a timer, and it's a time on delay kind of timer. The A will come right in the input. So when I have the input, I delay that input for, let's say, for example, 1 second. And then I turn on an output called Z. Okay, and this is just to show how we do things inside a function block. And then some of the few things that we need to understand in the function block is the retain. Now that retain configuration is what keeps that information stored when the PLC is turned off or powered off. Keep that in mind. It's not to keep it stored while the PLC is running. It's to keep it stored when the PLC is powered off. So when we revive the PLC, turn it back on or give it power back, we can see the same value that we left in here. And what we're going to do here is say, for example, put in a counter. So this is the variable connected to a counter. Nope. Does it do an integer? So IEC counter. And what we're gonna do here is ACTU. I'm going to put in the counter, and what's going to happen here is this is a preset value, the preset value that will turn the output on the counter, we're going to say it's 100, and then this is the reset. Input that we will feed to the R, and then the count up will be the Z. Okay. Now what we're going to do is we're going to turn this counter on. We want it to be retained. Now when we say retained, that means if we count to 17 and for some reason we turn off power to the PLC or to the machine, when we turn the power back on, we will still see that 17. It will not reset, it will not go away. So basically we're storing it in case of a power outage. Now we're going to turn on our simulation, and this icon is basically turn on the PLC sim, and since our network is the PNIE 1, then our PLC will be at PNIE 1. Consider as trusted device. At this point it's compiling my program and downloading it to the simulation or PLC sim. Now I want to turn my PLC on. My PLC is on. Minimize it. Now I just downloaded my program, and if I go online with my program, you will see that nothing is happening. What is going on here? Remember, we said that in order for any program to run, you have to call it from OB1. And what we're going to do here is call it. Now it will ask for its own data block, and the reason for that is it needs a memory to store its data because it is a function block. It's not a function. In case of the function, it will not ask for this. So we're going to tell it, okay, go ahead. Now the A, we will say, okay, we'll give you M100.0 for your A, and then M100.1 for your reset, and then the Z will be M100.2. Rename the tag, name it A. Rename this tag and make it reset. And rename this tag to make it Z. Okay. Now, since we did this, we download to the PLC and we'll see what happens. We can see that OB1 is calling my block. Going back to this block or inside my block, this is what's happening. Now what we will do here is we will split them, and that will give me the ability to modify my A is turned on after 1, the Z after 1 second, Z will be on, and then Z will count 1. So every time Z counts up, the counter. 4, 5, 6, 7. Okay, let's say this is 5. Okay, so you can see it turned on, but we want to see it how, basically we want to see how it happens live, so we have to reset. So when I turn the reset on, you can see this guy is on, and that resets the counter here, where now I can count 1, 2, 3, 4, 5. And when it turns 5, the output is on, regardless if the Z is on or not. The Q here is basically saying that I counted and I hit my preset value. That's basically what we're saying here. Okay, so now what we did was calling a function block, right? We wrote a function block, we called it, and everything included. Now, what if we can do all of this in the HMI? Let's do that. We will go and say, we're going to unsplit. We don't need these guys. What we're gonna do here is go to add a new screen in the HMI, and what we will do is add a button and then add an IO field and another button. This button, we'll call it A. This button, we'll call it reset. And this IO field will be the counter. And then we're going to add an indicator next to the IO field. And then this guy, we will add a little text in the middle right here. We call it Z. Okay. And you'll see the reason I'm doing all this, so I can have access to my indicator color, basically. So now, what I will do is open my tags, transfer all my tags to here. From the PLC. And here's what I'm going to do. I will look at my, not here. I will look at my main program, and what I need from here, from this main program, is, so I'm going to do something here that is not recommended, and I will show you what to do instead right after that. So I will transfer this guy to the HMI. So A is in the HMI. Let's do this. Okay. Reset is in the HMI, and Z in the HMI. Now, where is my counter? My counter resides right here in this block. So if I open this block, I can see this is the counter. And my counter is the CU, basically, the counted value. Now, what I can do is I can take this and drop it here. This is a really bad idea. This is not recommended to access the instant, we call it the instant DB, right to the HMI. Instead, what we're going to do, if we want to read the counter, we're going to go back to the block, modify or add an output, and I'm going to call it a counter, and that counter is going to have my counters data type, so that will be an integer. Counter output. What I will do is feed it right here. So now I'm ready. I have an output. I'm calling it a counter output. If I download everything, and it will ask me, you have to reinitialization of the block because I modified the data in it. So basically I added parameters, and then when I come to the OB1, I'll find there is a counter output. And with that counter output is basically an integer data type, and with an integer data type I will need to have a word. So MW 102. Rename it. Counter output. All right. Now that counter output I'll bring to the HMI tags. All right. Now I will look at my screen and I will say my A when I press it, I will say set bit and a tag, and basically the tag is, why is it HMI tag 1? Nope. Okay, I don't need this guy. I need A. So you can see I don't have A. Okay. So now I have my A. Boom. And remember, I want to hold the A, and then when I let go, I want to reset it. And then this would be set bit in a tag or reset bit in a tag, and that will go to tag A bit number 0 because it's a 1-bit kind of a tag. Same thing I will do here. I will say set bit in a tag, and that is a reset. And then I would say reset bit in a tag, and that would be the reset bit. Now what this is basically doing, it allows me to keep the reset bit on while I'm pressing, and to turn it off while I release it. Okay. Now I get to the counter where I display my counter. basically I will say that mode is output, and the processed value is a tag, and that tag is basically my counter output. That's all I need. And then I look at my Z indicator, and I will say that I need to alternate the background color according to my tag, and that tag is Z, and it will basically it will basically be grayed out when it's 0, and it will be green when it's not 0 or 1. So what I'm going to do is, I just added this in the alternative color. I will need the background color. So when it's 1, I need it to be green. And it's a read-only tag.